This video file is recorded in Sabancı University during the recitations for the CS201 Introduction to Computing course, as it was given in the fall 2016 semester.
A new example. Let me show you the output of what you should do. So it's this one, spell checker. You can copy paste everything about. First, let's delete the data that we don't need with the previous examples. Now go to this folder, spell checker, and copy paste everything from that folder. So I'm copying it, paste it to the solution folder here, and remove the codes that we don't need. Just add the newly added codes. So we'll need the string utilities, the prompt, the spell checker with vectors, and this is it. Now let's see what is this guy doing. You see here in the solution folder, this is the solution folder, you have only two txt files, data, and this is data. It's a kind of random text with some mistakes, grammatical mistakes in it. They were written on purpose. And you have the longer data txt. There are no mistakes here, but we will find them. And there's also a vocabulary. This is the vocabulary, words point that. A file with it's basically a dictionary with all English or most of the English language words, or at least the most used words in English are here. We have thousands of words basically. Now our job will be the following. You can see there are some mistakes here. Like, this is a pencil, but I'm not a tomato. Tomato is wrong. Or there's some, actually this potato is wrong. It's not written well. And how we are going to do that? We are going to check each of those words with a dictionary. If there is no match, that means that that word is misspelled. It's not spelled correct. It's misspelled. Also this one, now the file ends. This is not an English word. So we are going to print all of them. You see we don't have any output here. That's why I'm going to run the code. And I'm going to give data.txt from this folder, data.txt. Now it asks something like, do you want sequential or binary search? I'll say binary first. And it's being processed. And it's ended. Now let's see the output here. This is the output, spelled data. We have the misspelled words. The misspelled words are the following: potato, salad, meaningful, just, example. Why? Because we don't have them in the dictionary. We don't have them here, okay? If we cannot find them here, that means that those words are misspelled, okay? But as you can see, the dictionary has thousands of words. And it takes a lot of time to find, especially, let's say this. Okay, I'm going to run the program again. And we're dealing with data, but let's write system pause here, because we know we are finished at that time. So I'm writing system pause in the end. I'm running the code again. I give data.txt. Now the search is going to be binary, and it's working. Because I'm searching the whole library Now it's finished. Okay. Now let me do something else. Let me do the same example. And I have data.txt. And I want the search to be sequential. We are going to see in a while what's the meaning of those words. So it's going to be sequential. You remember binary took like 5 seconds, but this sequential search is going to take more. Sometimes much, much more. Okay, it's finished. It finished relatively fast, but it was more than the binary because this student, this data here, data text, is kind of small. Now, if we use larger data, we will need more time to finish our program. So there is another data here called longer data, and just imagine for each of the words in this file here, we are going to check the whole dictionary, and the dictionary has thousands, tens of thousands of words. Okay, and it takes a lot of time. We will have a timer for this stuff, but not in this example. So again, now I want to check the misspelled words in this file in the longer data.txt. So I have longer data.txt. I want to do a binary search. I wish we had the timer here, but anyway, even you can see the difference. Of course, it's going to take much more time than the data.txt. It finished, okay, in let's say 5 seconds, 10 seconds or so. But if I use a sequential search, it's going to take much more. So the name of the data was longer data. This is it. Longer data.txt. I want to do now a sequential search. It might take even like a minute or so, even more than that. And we are going to see why it is the case. For sure it's more than binary. You can even feel it. You don't have to measure the time with chronometer or timer, whatever. So it's still working. We're trying to find the misspelled words. It really takes a lot, but yeah, eventually it finished. It took like much more than binary search. We will see in a while what's the problem. So the program finished. We have our result here. So spelled data, the misspelled words are this one for the data file, and the misspelled words for the longer data file are here. Basically, those are words that are part of the English, but we didn't have them in the vocabulary. There are no grammatical mistakes here. This is okay, shouldn't, don't, but we don't have them in the vocabulary, in our dictionary. That's why we have them here. But they are not a mistake, okay? Raikkonen, Massa, Kubica, those are, if you know, Formula 1. Those are F1 drivers, but they are not in the dictionary, okay? If I write my name, it's not in the dictionary, it will be a misspelled word. But let's see what are we dealing with in this example here. Now, let's see what was that stuff, binary and sequential search. Let's say that we have numbers like 1, 2, 3, 4, 5, 6, 7, 8. Or let's say we have from 1 to 4. This is the sequential. This is the binary search. Let's say that we are looking for number 4. With sequential search, we start from the beginning and we search them one by one. Is this one that we're looking for? No. Is the second number what we're looking for? No, no, no. So in the worst case, with sequential search, how many searches do we need when we have 4 elements? In the worst case. How many? I mean, sequential, we start from the beginning and we check. No, 2, no, 3, no, 4, yes. So how many searches did we do? Comparisons? 4. Binary works like this. You always go in the middle. Let's say you go to here. And you compare 2 with 4. Is 2 equal to 4? No. And you compare whether 4 is greater or smaller than 2. Okay? If it's greater, then you check for this part here. Otherwise, you check for the other part. Okay? So, we start with 2. One comparison. It's not the same. Then we go here. And we say, okay, now let's check it with 3. Is that the same? No. Do we have to check it with 4? We are sure that since we have 4 elements, it's going to be 4. So how many comparisons did we do? We compared 2 with 4 and 3 with 4. So how many comparisons do we have? 2. Okay. Let me erase this stuff. So we have here a number of elements. When we have 4, we have 4 here, 2 here. Let's check it when we have 8 elements. So this is our array. 1, 2, 3, 4, 7, 8. In the worst case, how many checks should we have in sequential search? 8. What about with binary search? In the worst case, how many? Let me write all of them. So it's 5, 6, 7. We are looking for 4. We go in the middle. Let's say we are looking for 8 now. We go in the middle and we compare it with 4. This is one comparison. So we have the counter here. This one. 4 and 8 are not the same, but we know that it's in this half here. We go here again to the half of this half here. Okay. Compare it to 8 and 6. It's a mistake, so we have 2 comparisons. And we know that it should be in this half here. Now we have 2 more elements. And we compare 7 and 8. We have 3 comparisons. We see that it's not the same, but we don't have to compare 8 and 8 since we have only 2. So how many comparisons did we have? 3. What do you think about when we have 16? How many comparisons in the worst case do we have in the sequential search? 16. What about the binary? It's like this. So we saw that now we go from 9 to 16. From 9 to 16 we have 8 elements. One more comparison, and let's say we are looking for 16. So we'll start from 1 to 16. We will start comparing 16 and 8. They're not the same, and the element we are looking for is in this half. So one counter is used. How many elements do we have in this half here? How many? From 9 to 16, how much is that? 8. But for 8, we saw that we have 3 counts, 3 comparisons, okay? Plus 1 here for this one, so we have here 4, okay? So as you can see, can you come up with an algorithm, I mean a formula with the sequential and with the binary search?
It's probably to the power of number of elements.
Or even better, it's like this. Sequential, if the number of elements, let me write it as n. So sequential is always equal to n. But binary is equal to the logarithm of n with base 2, which is written as LGN. Okay? So you said 2 to the power, yeah. The inverse function of logarithm is exponentiation. Okay? So which one is better? n or log n? Log n is better. You have much less comparisons. Okay, so this is the difference between sequential and binary search. If you're going to take again the algorithm course, you'll deal with these issues much more in that course. Okay, so since your job will be not to write programs that work correctly, but to write programs that work fast. Okay, and here is the number of input. In our case, the number of input is the number of words in the dictionary. But we have a problem. In order for the binary search to work, can you see what's interesting about this sequence of numbers? 1, 2, 3, 4, 5, 6. What is it? Can we work with the binary search here if the sequence of numbers 3, 7, 4, 1, 9, 2? Can we apply the binary search here? No. So why we can apply it here and why not here? What's the reason about that? Because this one is sorted. Yeah. Researchers deal a lot with those kind of things, and it has been proven that when you want to search a certain sequence of words or whatever, you should first sort it. It's better to sort it and then search for it. Why? Why it's the case? Because you search for a certain sequence of words or numbers much often that you insert. Okay, so you sort it once and you are going to search maybe thousands, hundreds of thousands of times. Okay, if you're going to use it only once, yeah, you don't have to sort it. You can use a sequential sort maybe, and it's enough. But if you want to use it many times, it's better to sort it and then to use it. Okay, so this is what Google is actually using. Or the computers. They sort things in a way, but you'll see it how. Not like this. Now we saw one kind of sorting. It was simple sort, select sort. Now we are going to see another type of sorting, which is called insert sort. And we are going to use insert sort here. Remember, the sorting problem is very important, it's very hard, and we're going to deal with another example during this class, I think, for that. And if you come up with an algorithm that makes, that sorts the lists, the vectors in a quick manner, then you are doing a very important job. Probably you'll get there's no Nobel Prize for informatics or IT, but there's something which is called Turing Award, which is the compatible stuff, okay? If you come up with a sorting algorithm that works fast, then you're doing an awesome job. Because it's estimated that 70 to 80% of the computers are doing some sorting job. And you can see it why. Because you don't want to do sequential sort, you want to do sequential search, you want to do binary search, but in order to do binary search, the list should already be sorted. Now let's see another algorithm which is called insertion sort. We will use the same array, namely 3, 7, 2, 1, 8, 9. We saw it. So this is a sequence of one-digit numbers. 3, 2, 7, 1, 8, 9. We want to sort it. Here we will apply an interesting logic, which is the following. We will start with the first number. If you have only one number in the list, that number is automatically, by definition, sorted. So we'll start with 3, and we will try to insert another number. So we have 3 here, one number. Now we'll go with 2 numbers. So we are here now. 2 should be inserted here. Okay? 2 should be inserted here. So which one is greater, 2 or 3? 3 is greater, so we will have 2, 3. Okay? Now, this is pass 1. Pass 2. In this sorted sequence, we want to add another number. Insert another number, which is 7. So we want to add 7 here. And how we are going to do that? Well, 7 is the greatest of them. So we have 2, 3, 7. Okay? Now, pass or iteration 3. We have 4 numbers now. We want to insert 1 in this sequence here, 2, 3, 7. And you can see 7 is greater than 1, that's why 7 will be here. 3 is greater than 1, that's why 3 will be here. 2 is greater than 1, 2 will be here, and 1 will be inserted here. Okay? 8. That's why this is called an insert sort. It's like inserting a number into an already sorted list, but the list increases. We insert 8 now in this. Okay, so pass 4. It's going to be, we have 5 places. 7 is not greater than 8, then we just put 8 here, so we have 7, 3, 2, 1, and so on. Okay, you see it's already, and 9 comes in the end, in the pass 4, pass 5. So this is insert sort. We're going to see it in algorithm because we are going to sort the list of the words, but the list of the words from the data that we're going to read, longer data or data. But as you can see, the words here in the dictionaries are already sorted in the English dictionary. So we start from A, continue with B, words that start with B, C, and we end with Z, of course. Now let's go to the program and see what is this program doing. We include all the necessary libraries here. Then we have some functions here. One of them is check word binary. This is what we do. We take a word as a parameter. We send it as a reference, and it's a constant. And also we send a vector, which is called the spelled vector. Spelled vector basically is the vector of the English dictionary that has thousands of words. Okay? We take the words then and we put them in the vector. We'll see that in May. This guy here, we'll send them as a reference because if we make another copy, we might not have place in our memory. But we want to make sure that we're not going to change their values. That's why we put this const here. Okay? Now what do? We apply the binary search logic here because we know that this spelled vector is already sorted. So, you remember here I started from 1 to 16 or from 1 to 8, meaning low was 1, high is 16. We go always in the middle and we compare the middle with the word that we want. If you don't find it, then we check the word that we want, whether it's in the upper half or the lower half. So this is how we do it. So we start with low, which is 0, high, which is the size of the vector, meaning we start from index 0. The vector has it again. The spelled vector, this vector has all of the words in the English language. It starts from index 0 and it goes to up until size -1. Okay? We find the middle. We do this loop here while low is lower, smaller, or equal to high, because sometimes if it's the opposite, I mean, we check it from 1 to 16, the middle is 8, the middle, and we don't find it. Then we check it between, let's say, 1 and 8, the middle is 4, we don't find it. We check it between 1 and 4, the middle is 2, we don't find it. We check it between 1 and 2, we don't find it. Then low, this high is going to be 2, or low is going to be 2, so 2, and high is going to be 1. Basically, they swap their places, meaning that we didn't find the word that we are looking for. For instance, if we're looking for 1.5, we cannot find it here. That's why we do this loop here, meaning that we haven't found it yet. Middle is low plus high divided by 2. Now we check if the spelled word is in the middle. If it's in the middle, very nice, we return true. Otherwise, we do this one. We check if the spelled word, if the word that we're looking for is smaller than the spelled word. If it's smaller, then we are looking in the upper half. And this is how we do it. That low becomes mid in the lower half, actually. Low becomes mid plus 1. Basically, let me show it to you here. If this is what we are looking for, so this is 5, 6, 7, 8. Let's say that I'm looking for 3. So initially I take the middle of 1 to 8 is 4. This is not equal. And now I'm trying to look either in this half or this half. But this 3 is smaller than 4. That's why initially low was 1 and high was 8. Okay. But if 3 is smaller than 4, then high will be 4, and I will be looking in this part here. Okay. However, if I'm looking for, let's say, 7, and I see that 7 and 4 are not the same, then I should be looking for this half here. That's why low will be from 5, or maybe from 4. But that means that I'm looking at this half here. So with this piece of code, this is what we are doing. If we find the vector, okay. If we don't find it, if the word is greater than that, than the word in the vector, then low becomes mid plus 1. Basically, this low is not here, but mid, which was 4 plus 1, it becomes 5. So we are looking in this range. Of course, we can. This is the lower half, the second half. We can look in the upper half. Otherwise, high becomes mid minus 1. Okay, so high might go here, and we can look at this upper half. And this is in a while loop. We keep doing this stuff up until we find the vector. When we find the desired word in the vector, if we find it, we return true. However, when this condition happens, basically low will come, so high will be here, then low will come here, then high will go here, low will go down, high will be higher than low. When this happens, that means that we didn't find the word. This while loop will not be true, so we go outside from the loop and we return false. We didn't find it. Okay, this is about binary search. Sequential search is much easier. We go from 0 to the size, and we check if the word we are looking for, which is again sent as a parameter. So vector word, I mean we could have done it in an easier way, but never mind. So spelled vector of I, and I is from 0 to the size, 1,000, 5,000, 10,000 words, how many words did we have? If the words are equal, if there's a match, then we return true, that we have found it. Otherwise, if we go outside of the loop, that means that we hadn't found the word. That's why we return false. Okay? Again, if we return true, the function finishes. We might have millions of lines after return. If we return only once, whether true or false, a Boolean value in this case, the function finishes. So if we don't return true here, that means that we didn't have a match. That's why we return false. But this is the sequential search. It's easier to write, but it takes more time. Easier to write and understand, of course. Now insert sort. You remember the algorithm with the insert sort there? So this piece of code is doing exactly that, okay? We say initially that we start with sorted list, sublist, and we put elements in that list, one by one. So that's why we start here with 1, not with index 0, because the first element is already sorted. And we put it to the list accordingly. I mean, if it's smaller, then we move it. Otherwise, we don't move it and put it to the corresponding place, okay? I just explained the main idea, the algorithm, the logic behind the insert sort on the board. And this is the code, how you do it. Of course, you can come up with your own code, even with your own algorithm. Again, the purpose of this algorithm is to sort a vector of strings, of words, basically. That's why we send it as a parameter, because we want to see the changes in main, and we send the size of the vector. This is how it's done. Now we should, in order to sort words, of course we should read them. We read them in this file here. It returns true or false. True meaning that, I mean, you remember the words.dat file. We had the English dictionary there. Well, we take the words from that file and we put them to a vector. This is how we do that. Since each word was a new line, we use the getLine function. We put it in a word, and then we use pushback function to push all the English dictionary words in the vector, which is called spell vector here, okay? Of course, if you cannot read it, so we open words.dat. If we cannot read it, we return false. That false means that bool is true if everything is okay, meaning if we succeeded in extracting the data from the file and put it into the vector, we return true. If we don't do that, we return false. So if we cannot open the file words.dat, then we return false. Otherwise, if we can open it and take the data one by one, using the getLine function, since again I repeat again, all of the words in the English dictionary were in a new line, in the words.dat file, we push them back. They are already sorted here. Input clear, input close, and if everything is okay, when this file while loop is finished, we have the spelled vector filled up with words of the English language, and then finally we return true, meaning that everything was successful. We have the desired data in the spell vector. So let's go with the main now, with the main function. We define file name and search type, strings, declare them. ifstream called input. Of course, we prompt for the user to give the name. We open the file name. If we cannot open it, we return 0. Now we prompt the user to give the search type. It's either sequential or binary, and we assigned it to the search type, the string which is called search type. If the search type is not binary or sequential, it's not either of them, then we say irregular search type. I mean, well, what are you looking for? We return 0, but basically we finish with the program. If it's one of them, then we want to put the result in a file called spelled. You see here, we have spelled data and spelled longer data. So the output name will be basically same as the input name, with this part as part of the name. So spelled and data or spelled longer data. We try to open it. Basically, we open it here. We declare a new vector, which is called spelled vector, which is of type string, meaning each of the elements is of type string. Here we read all words. You remember the read all words function here. So this one. If we cannot read all of them, we print out cannot read dictionary file exiting. Okay. If we can read them, then this is what we do. We see whether the search type, so if the search type was not binary or sequential, we finish with the program. But if this is not true, that means that the user entered either binary or sequential. So if the search type is binary, then we sort the spelled vector. Actually, we shouldn't sort it because it's already sorted, but just to make sure that maybe it's not sorted, might not be sorted, we sort it here. Because, I mean, if the search type is binary, we have to sort it, because binary search works only with sorted vectors. If it's not binary, we don't have to sort it. You write this one, misspelled words. Basically, this is misspelled words. So we write it to the output file. And then we read words one by one from the input file. Let's say this one, data.txt, or which one? You know the function strip punctuation. If you have comma, semicolon, whatever, punctuation signs in the beginning or the end, you get rid of them. You use the to-lower function because you don't care whether they are capital or uppercase, lowercase. I mean, lowercase a, uppercase a is the same. We don't care about them. Again, we strip punctuation to the original words. And now if the search type is sequential and the word does not appear in the dictionary, then we put it to the output file. Of course, if the search type is binary and it does not appear in the spell vector when we check it in binary form, we append it, we write it to the output. Okay. Here we use the word check word sequential. Here we use the check word binary. So, if the search type we have entered is sequential, and the word after being sequentially searched is not in the dictionary, then write it to the output. Okay. Then we are finished with the program, and this is it. I know that it's a bit tricky. I don't expect from you to understand 100% here, but if you go at your home and you just see the code, you'll need maybe like 5-10 minutes to understand what we have been talking here. And this is my aim, basically. It's not as tricky as it looks in first sight. Okay, it's easy. Again, how many of you understood it? But be honest. We have like 50-60% of you. Do I need to go through it again? Yes or no? Yes? No? I mean, one of you says yes. I can go through the code again and explain it to you. If no, maybe we can take a break of 5 minutes. You can ask during the break what you want, and we can continue later on. Okay, let's take a break then.